Well, we're almost halfway done. This lesson is about static class members. Static class members allow you to share information among objects of a class without revealing it to the rest of the world. Static member functions are a more efficient way to call certain types of functions. For example, say I have a basket of apples, which I do. Let's also say that there is a variable that defines ripeness, and say that when an apple reaches a certain state, we'll say it's gone bad. And once that happens, all the other apples should know about it, so they can also go bad. In this case, one bad apple really does spoil the whole bunch. Suppose you want an object which holds a single word. Then you can turn a text file into a group of these objects. Also suppose you want any word to be able to know how many total word objects there are. You could solve the problem this way. Now, anyone can access word count to find how many words there are. There are two problems with this approach. The first is, since word count is global, anyone can modify it. There's no safety. The second problem is word count is in the global namespace, which means if you bring in some other library which uses the same name, not unlikely since we are dealing with text, there will be a clash. You may think to solve the problem by bringing word count inside class word like this. The name is no longer global, and the data is protected so only members of the class word can read or modify it. However, it doesn't produce the desired effect because storage for word count is different for each object. C++ solves these problems by adding yet another meaning to the keyword static. In C, static has two meanings. When used to define a variable outside all functions, it means the variable has internal linkage. That is, the variable can only be accessed within this file. If the variable is defined as static or global in another file, there will be no clash and different storage will be reserved for both variables. The second meaning for static in C occurs when it is used to define local variables in a function. A static variable is not an automatic. That is, it is not created on the stack, but instead in a special static data area. This means that its value is held, it is static, between calls to the function. In C++, a static data member inside a class is similar to this second definition. A static data member is kept in the static data area, and there is only one variable allocated for all the objects in a class. Put another way, each object in the class shares the same variable. This is exactly what we need for class word. Now there's a question. Since all the objects have access to the static member, who is responsible for reserving storage and initializing it? You cannot do it in every constructor since every object created would then reinitialize the static member. There is a special way to create and initialize static data members. You must create a definition outside of all functions. This looks somewhat unusual, because you must not only give the variable name, but also its type and specify the class using the scope resolution operator. If you have a static data member which is a class object, you define and initialize it in a similar fashion. For instance, this defines a word object called blockName, which is a static data member of class textBlock, and hands the string textBlock to the constructor. The initialization of static data members occurs before main is entered. If the member is a class object with a destructor, the destructor is called after main exits. Now suppose you want to read or modify a static data member. You can access a static data member just like any other member, so you can use a normal member function like this. However, when you call count, you must then call it for an object. That is, send the count message to a particular object. And this, the address of the object, will be secretly passed into the member function. While the extra overhead may not be a problem, there are some cases where the reduction in efficiency is unacceptable. This is true not only for functions which only access static data members, but for any function which acts for the class as a whole and doesn't need to access members of a particular object. We can eliminate the extra overhead of passing in this by making the function a friend. Now count is a global function which has access to private static data, but it doesn't have the extra overhead. However, the function is no longer in the scope of the class word, so if someone introduces the name count by bringing in another library, for instance, there will be a clash. C++ allows you to surmount these problems in an elegant fashion. You can define a member function as static. This meaning is close to the one for static data members. The function is for the whole class and not just one object in the class. The this pointer is not secretly passed into a static member function. Thus, you don't get the extra overhead, but you also cannot access anything but static data members and static member functions. Since the function is a member of the class, its name is hidden inside the scope of the class and will not collide with global names. In addition, you have the notational convenience of associating the name with the class, so it's more obvious what the function is supposed to do and that it may be affected by changes to the class. Static member functions are defined just like any other member function. You can call a static member function in two ways. First, just like any other member function, and secondly, and this is unique to static member functions, by specifying the class using the scope resolution operator. This can be an important way to call the static function because it doesn't require reference to an object. Calling a normal member function for an object when it doesn't actually use or modify that particular object can be confusing to the reader of the code. So that's how static class members and functions can help make your life as a programmer easier. In the next lesson, we'll talk about another great advantage of C++, the ability to create and destroy objects at runtime. Sometimes when you're designing a system, you don't know everything up front. Oh, all right, a lot of times you don't know everything up front. Anyway, that means you need to be able to create and destroy objects at runtime instead of at compile time. With C++, this is easy. We've already looked at how simple it is to tell the compiler to create objects. You give the type of the object and a name and sometimes an argument list. The compiler creates space and calls the constructor to make an object called S. When you create an object this way, you know all the information about it at compile time. There will be times when you don't know the quantity, type, or lifetime of the objects you need at compile time. And you won't know it until it is somehow obtained at runtime. For example, say you're designing an air traffic control system. Each plane has a position, a direction, and a velocity. They come into the system and leave it at different, unknown times. So they must be created dynamically and based on information which simply can't be known at compile time. The creation and destruction is complex, and you want to guarantee it happens properly under all conditions. In C, it is possible to allocate memory at runtime using the ANSI C library functions malloc and free. Malloc returns a pointer to a piece of memory in a special data area called the heap, which is only used for dynamic memory allocation. You call free to release the memory when you're done with it. In this example, you have the options of how big to make the array and when the array will be created and destroyed. There are problems when using the C library functions for dynamic memory allocation. First, malloc just gives you a chunk of raw memory. No initialization is performed, so you might use the object without initializing it. Second, you cannot call a constructor explicitly. So even if we wanted to use malloc, we couldn't use constructors. When using free, there is nothing to ensure that a destructor is called, and you cannot explicitly call destructors. In C++, dynamic object creation is considered so important, it was brought into the core of the language with the addition of two keywords. The keyword new not only allocates space on the heap, it automatically calls the constructor for that object. Also, when you use new, the compiler determines the size of the object you're creating. This provides a more readable syntax. So instead of this, you get this. If plain is a class with a constructor. Since new returns a pointer to a live, initialized object, you are guaranteed the same safety with objects you create at runtime as you get with objects you create at compile time. In addition, both activities require just one line of code. The keyword delete is the complement of new. It automatically calls the destructor and then releases the memory to the heap. You use it by handing it the pointer to a dynamically created object. Deleting a null pointer has no effect. New and delete make it as easy to create objects at runtime as at compile time. You use the same constructor and destructor you use when creating objects at compile time. This means you can solve dynamic problems easily and safely. For instance, let's look at how to solve the air traffic controller problem. The concept of a plane is represented with a class. The destructor should do something appropriate according to the way the problem is being solved. Here's how new and delete are used inside main. While this is a great improvement, there's still a problem. The airfield array is not only a fixed size, but it isn't safe. It's an object, a region of storage, which has no guaranteed initialization and cleanup, and no access control to make sure it's used properly. The array is an example of the kind of problem you encounter when creating objects at runtime. What do you do with the pointers you get back? They have no name, and you need to store them somewhere so they can be accessed later. Placing them in a simple array is not the answer because the array is unsafe and has a fixed size. To solve this problem, object-oriented programmers developed the concept of a container class, also called a collection. This is a class which is designed to hold objects of some other class. We can make a simple container to hold planes. The function increase increases the size of the array without disturbing the contents. You can find its definition on disk. Notice that you can use new to allocate variables of built-in types as well as objects. There is no need at all for malloc and free in C++, but their use must still coexist in C++ programs so they can use existing C libraries. Now we can create an object to hold plane pointers and tell it how big to make itself initially. If it runs out of space, it automatically makes itself bigger. It's very much like an expandable bag. Virtually all collections have a way to put things into them. Use them once they're in, and to remove them when you're finished. There are numerous ways you might implement a collection, as a linked list, for example. But the user doesn't need to know how it works, just that it does the right thing. Here's how the collection is used in the air traffic controller problem. Not only is it much easier to read the code and see what is going on, the whole system is much safer. You know that all planes will be initialized and cleaned up properly, and you never need to worry about running out of airfield space.
Well, almost never. In this lesson, we've learned how dynamic object creation lets you deal with objects which don't exist at compile time. We've done this with new and delete, and with container classes which hold objects created this way. Next time, we'll talk about how to organize code for most projects you create, which, if you're like me, are large projects with multiple files.
All the stuff we've done so far in this course has been pretty small in terms of code. Most have fit inside a single file. But when you work on real projects, odds are they aren't going to fit in a single file. Your code will be a lot more maintainable and much easier to rebuild if you spread it out over many files, also called translation units. In this lesson, I'm going to talk about how to organize your code so that you can take the greatest advantage of C++ and to avoid costly errors. Now, both C and C++ use a concept called header file. A header file has declarations that are used in more than one place.
You include the header file any place you want to use the names in that file, both where the names are defined and where they are used. As discussed in Lesson 9, a declaration gives the compiler information about a name. In C++, a header can include any of these declarations. Note that none of the information in a C++ header allocates storage. Since a header file is included in several files, which are later linked, allocating storage in a header file would cause multiple definitions across the files where the header was included. The linker wouldn't like this, so the first rule for header files is they can only include declarations. In C, it is possible to use a function without declaring it first. Because you may use the function incorrectly, or the compiler will make incorrect assumptions, C++ requires you to declare all functions before you can use them. You could declare the function by typing in its prototype, but then you would get no check between the place where the function was defined and where it was used, even though type-safe linkage would catch it later. Therefore, the second rule for using header files is you must include the header file everywhere it is used. All functions should be declared in header files. This provides a safety check when the compiler compares the declaration in the header file with the definition. By including the header file where the functions and data are defined, you automatically ensure consistency across all translation units. So the third rule for using header files is you must include the header file in the place where definitions occur. You can name your header files anything you want, but the custom in C and C++ is to use an extension of .h. You might even see header files with no extension at all, or older code, or code from other systems which use .hpp or .hxx. Files which contain definitions and which are compiled to produce .obj files are usually given the extension of .cpp, but older code, or code from other systems, may use .cxx. Since you are forced to declare a class any place an object of that class is used, and any place member functions of that class are defined, you are basically forced to put the class declaration in a header file in C++. Here's how you usually organize your code. Notice that the interface to the class is defined in the header file, but the implementation is defined in the definition file. This separation of interface and implementation can be very important. Since the files which use the class get enough information for proper compilation from the header file, you can define the interface before you specify the details of the implementation. While the linker will be unable to resolve function calls until those functions are defined, you can run the compiler to make sure the usage is correct. Thus, you can prototype the framework of a system before filling in the details. Although you can give a class name declaration multiple times, you can only give a class declaration with a body once for each translation unit. If you try to redefine a class body, the compiler considers it an error because one body might not agree with another, and there must be no ambiguities. This can become a problem when you are dealing with a lot of classes, especially when one class uses another. You may end up including the same header file several times in the same translation unit without being aware of it. Now the file allball.cpp will get an error during compilation. In a library, this is especially problematic, since the user of the classes may not have control of the files which cause the multiple definition error. There is no mechanism built into the language to solve this problem, but you can do it easily with a little discipline. The trick is to insulate each header file using the preprocessor. The format you choose for naming may be different, but here's one approach. The first time a header file is included, its special name, created by modifying the file name, has not been defined, so the body of the file is included. This inclusion causes the special name to be defined, so the next time the file is included in a translation unit, the preprocessor doesn't include its body. Now your header files can even be part of future classes without your having to worry about multiple class declaration errors. If you organize your code this way every time you write a program, you'll save yourself a lot of headaches. But as you can see, I'm kind of a stickler for neatness. Next time, we'll talk about one of the most powerful attributes of object-oriented programming, inheritance, which allows you to create new types using existing types and save yourself a lot of work in the process. Let's talk about inheritance. Inheritance is one of the best things about C++. So far, all the classes we've created have been built from scratch, which is probably the way you've been working when you want to add new features to a program, since it's usually just as easy to write new code as to change existing code, debug it, and all that other rigmarole. What you want to do is be able to add new features to a program without changing the original code. And that's what inheritance lets you do. In C, if you have the library of code and its source, which isn't always the case, as you well know, you can make changes. But first you have to have a copy of the code. As you make modifications, you need to understand the internals of the functions that someone else may have written. As you do this, it's a given that you're going to introduce some bugs. These may or may not be easy to find, so you end up with two bodies of code, the old debug body and your new body of code, which contains the old code in some form, plus additions and changes, and of course new bugs. Future changes mean more copies, and the amount of code you need to maintain increases, but without an equivalent increase in functionality. Creating new data types, that is, classes, is the fundamental activity in C++, since we use types to model the problem being solved. When we think about changing or extending code in C++, it's natural that we think not in terms of data or functions, but in terms of classes. Thus, reusing code in C++ means reusing classes. It's very common that an existing class that you or someone else has written and debugged doesn't quite do what you want. In C++, you can make a new class from an old one using inheritance. When you inherit, you say, this new type is that old one plus some data and functions. With inheritance, you don't make a copy of the existing member functions, you just use the ones that are already there. You can add new data members and function members. You can also change the meaning of existing functions by redefining them so they have a different behavior for your new type. You don't even need the source code for the member function definitions, just the header files containing the class declarations, which must always be available to use the class in any case. This means you can inherit from any vendor's class library, whether they provide source code or not. Let's see how the syntax works. First, suppose we have a simple class which represents a signal sent between objects. A signal is pending until it is cleared. If it is destroyed before it is handled, you get a message from the destructor. Now suppose we want a new type of signal which carries a message string. We could take the above class, make a copy, and modify the copy to create a new class. Instead, with inheritance, we say this. The class declaration says, class message is a type of signal. This means that message inherits all the characteristics and behaviors of signal. That is, all the member data and functions which were in signal are now in message. For instance, you can call the function status for a message object, even though it was defined in signal and you don't see it in message. We've also added three functions. The constructor is, of course, unique for the class message, since constructors always know specific information about the type they are creating. We've added member data, which is a character buffer, and an access function to allow that character buffer to be read, but not modified. Notice the return pointer is const. The third function is a redefinition of the base class function clear. If you call clear for a message object, the compiler will call this version of the function rather than the base class version. This means you can change the meaning of existing member functions during inheritance. But what happens if you still want to call the base class version of the function? If you simply call clear inside a function of the same name, you'll get a recursive function call. To tell the compiler you want the base class version of the function, simply use the name of the base class and the scope resolution operator. Notice we must include the header file for the class signal before we can derive a new type for that class. The compiler must see the base class declaration before it can make a new type from it. The size of the new type is the size of the old data structure plus the size of the character buffer. Derived class objects contain all the data structures of the classes they are inherited from. Class signal is declared public. Remember that classes default to private. Inheritance with classes also defaults to private. Private inheritance means that all public members of the base class are private in the derived class. Sometimes this is what you want, but not usually. To force all the public members to remain public in the derived class, you use the public keyword during inheritance. None of the private members of the base class can be made public in the derived class. This would mean that you could break the data hiding mechanism through inheritance. If a base class member is private, the only way you can modify it is via the base class member functions, which have legitimate access. If you want to make members of a class hidden, but you want to give access to derived classes, you must make those members protected.
So, inheritance works just a little like it does with humans. With C++, new types inherit all the attributes of existing types, plus whatever new data or functions are needed. Fortunately, my daughters haven't inherited all my attributes. Anyway, in this lesson, we've created new constructors for derived classes. But how are base classes properly initialized? In the next lesson, you'll learn about base class constructors.
In Lesson 14, we learned about inheritance. Inheritance allows you to create a new class by adding members on top of an existing class. In this lesson, we'll show how to ensure that the base class is properly initialized. We've seen before that proper initialization is a fundamental concept which pervades C++. It's no different during inheritance. All base classes must be properly initialized before the object is turned over to the user. In a base class with no constructors, or with a default constructor, the compiler will call the default constructor if you don't. But what if there's no default constructor, only one with arguments? How do you call the constructors for base classes? The solution requires an addition to the syntax of constructor definitions. You explicitly call base class constructors using the constructor initializer list, which occurs after the function prototype, but before the opening brace of the function body, like this. The colon after the argument list indicates the beginning of the constructor initializer list. The list consists solely of constructor calls. Often, you only have a single constructor call, but you can have more than one if you are using member objects, which we will discuss in Lesson 17, or multiple inheritance. The constructor initializer list allows you to explicitly initialize base classes by passing arguments to their constructors. Let's look at a more interesting example. Suppose you derive a new class called Cycle from the message class in Lesson 14. The message class has no default constructor, only a constructor which takes a character pointer as an argument. Thus, you cannot let the compiler automatically call the constructor, since it wouldn't know what to do. You must call the constructor for message in the constructor initializer list for Cycle. Here's what it looks like. You simply give the name of the class and the arguments. It's quite simple and intuitive. You'll notice we are using a local enumeration in the class. Enum state is public because otherwise the class user couldn't access it, as we do in main. When you refer to an enumeration name, which is inside a class, you must give the class name and use the scope resolution operator. The advantage of using an enumeration locally to a class is that the names of the enumeration cannot clash with any global names. This is quite important because enumerations often consist of many names, so the possibility of a clash is significant. You may wonder about the order of initialization of base classes. Which is initialized first, the earliest class or the latest one? To find out, it is helpful to create an experiment. Here, we've created 3 layers of classes, each of which announces when its constructor is called. The output of this program is Thus, constructor calls always start at the base class and work their way out. This is important because any derived class constructor needs to assume that the base class has already been initialized, since you may do something in the derived class constructor which depends on a properly initialized base class. In this lesson, we've learned how to explicitly call constructors for base classes in the constructor of a derived class. In the next lesson, we'll look at the way destructors work when using inheritance. In the last lesson, we saw how C++ enforces proper initialization of objects when inheritance is used. Calls to base class constructors are either made for you if a default constructor is available, or you can make them explicitly in the constructor initializer list. C++ also ensures proper cleanup of objects. In this lesson, we'll look at the way destructors are called when using inheritance. Since there is only one destructor defined for each class, and there are never any arguments for destructors, you don't need to do anything special for destructors during inheritance. The compiler will automatically call destructors for base classes. Let's see how this works by creating a simple class which places a mark on the screen. The constructor takes the character you hand it and places it on the screen in the desired spot. The coordinates of that spot are protected, so they can be accessed by derived classes. The destructor goes to that spot and writes a space there to erase the character. Now we can derive two different types of marks, an X and an O, perhaps for use with a tic-tac-toe game. Notice that neither class has a destructor. The base class destructor, however, is automatically called in the two classes, so the objects are still properly destroyed. We can see this in an example program. You can see that the destructors are automatically called. What happens when we redefine the destructor in the derived class? Here's a simple experiment. Each constructor and destructor simply announces itself. Now we see two interesting things. The first is that even though both the constructor and the destructor are redefined in the derived class, both the derived class version and the base class version of the constructors and destructors are called. Contrast this with the typical function represented by f. The call to f causes only the derived class version of the function to be called. If you want the base class version to be called also, you must do it explicitly in the derived class definition for f. Note that constructors and destructors are the only functions which automatically call all the base class versions of the function. This is important because all the base class portions of the object must be properly initialized and cleaned up. Constructors and destructors are unique in some other ways also. You cannot take their addresses, and they don't have any return values. Whenever you deal with constructors and destructors, remember that they are special because they are performing the rather magical acts of bringing an object into existence and taking it out of existence. These acts are outside the normal flow of events, so the functions are unusual too. The second interesting point is the order of destructor calls. Notice that while the constructor calls build the object from the bottom up, the destructors destroy the object from the top down. This order is important because of what assumptions the functions must be able to make. Any constructor cannot know what is derived from it, but it must be able to assume any base class member function it calls will behave properly. This is only true if the base class constructors are called first. Similarly, a destructor must be able to assume that all base class functions will behave properly, which is only true if the base class destructors are called last. It's always important to remember that constructors and destructors are special. We've seen that they also act differently during inheritance. In this lesson, we've covered base class destructors. In lesson 17, you'll learn how to create new types with composition.
Derivation is when a new data type or class is inherited from an existing class. Derivation creates a class which is a type of, or kind of, another class. For example, don't worry, I have plenty of toys left. A car is a type of vehicle. This type of relationship makes sense, at least in a lot of situations. However, if you had a wheel class and an engine class, you wouldn't make a car class from either of those, because a car is not a type of wheel or a type of engine. A car does contain an engine, and it does contain wheels, and doors, and hubcaps, and tie rods, and floor mats, and radios. Anyway, to represent this relationship in C++, we use composition. An object is composed of other objects, as well as being derived from still other objects. In this lesson, we'll look at how composition works. So far, all class members have been built-in types: ints, floats, character strings, etc. We can just as easily compose classes with user-defined types just by creating an instance of a class inside the new class. Here's what it looks like. You can see that composition with user-defined types is as easy as using built-in types. That's the way it's supposed to be. Once you create a class, using it is almost exactly like using a built-in type. There is a difference, however. Built-in types don't have constructors and have nothing like private members, so we haven't had to worry about initializing them so far. But classes usually have constructors, which must be called. In addition, member objects in a class must be initialized before you enter the body of the constructor. Otherwise, the objects might be used before they are initialized. To solve this problem, we again use the constructor initializer list. As well as calling the constructors for base classes, we can also call the constructors for member objects. Indeed, this is the only place we can call the constructors for member objects. The form is identical to that used for inheritance. The constructor initializer list starts after the argument list and a colon, and ends up at the opening brace of the constructor body. When you have more than one constructor call in an initializer list, they are separated by commas. If you have a base class, or more than one base class in the case of multiple inheritance, you simply put the call to its constructor in the list, just like all the other calls. It's even possible to make a pseudo-constructor call for a built-in type in the initializer list. For instance, we could rewrite the above constructor like this. This has exactly the same effect as before, assigning the value of pass to passengers. Pseudo-constructor calls for built-in types are often used by programmers in place of assignment, although the effect is exactly the same. The choice is purely cosmetic. Destructors are automatically called for member objects just as they are for base class objects. Composition is a relatively easy concept. It's common sense. The only trick to putting member objects into a class is remembering to call their constructors in the constructor initializer list. Next up is a lesson where you'll see how you can build a model of the problem you're trying to solve by creating a family of types through inheritance. Throughout this course, we've looked at ways to encapsulate characteristics and behaviors. Inheritance and composition let us create new classes from existing classes. One of the advantages of object-oriented programming is that we can make programs model the real world, rather than the other way around. In this lesson, we'll look at how classes and inheritance can be used to model real-world problems that we hope our programs will solve. We'll learn how to create a common interface to a group of types, and to create functions which manipulate that interface. If we are trying to model the world in terms of types, we must consider that a type doesn't always exist by itself. It often has a relationship to other types. Although inheritance allows us to save effort and reuse code by creating new types from old ones, it has a more important role, expressing the way a family of types relate to each other. By dealing with a family of types,
Instead of isolated types, we can solve problems in a more general and powerful fashion. To see how this works, suppose you have a class which represents a dog. The function talk is a piece of code which is separate from the class, but that uses the class. Now suppose you discover you have more than one type of pet on your hands. Cats and birds can also speak, and they have other things in common with dogs. Wouldn't it be nice if you could represent the different types of pets in our program? This is where inheritance comes in. As soon as you see that there should be a relationship between several types, determine the common elements in that relationship and put them in a base class. All the types can then be derived from that base class. In the pet example, it looks like this. We can read the class description like this: all pets can speak. A dog is a type of pet which says woof. A cat is a type of pet which says meow. A bird is a type of pet which says cheep. Notice that although we are explaining the code, we are also explaining the relationships of the types in the real world. This is a good test for your design. Do the type relationships, characteristics, and behaviors make sense when described to a non-programmer? There's a problem with this program. Although the talk function still works, it can only work with a dog. It would be much more useful if it could be used with any type of pet. If we write talk like this, however, we won't get the right effect. The compiler will see that you are dealing with a pet object, so it will call the speak function for the base class pet. This has an empty function body, so nothing will happen. The crux of the matter is the compiler is deciding too early what function it is going to call when a message is sent to an object. In object-oriented programming, letting the compiler decide what function to call is referred to as early binding, since the function is bound early at compile time. What we would like is for the object to decide what function should be called rather than the compiler. This decision should take place at runtime. In object-oriented programming, this is called late binding, since the function is bound at runtime. With late binding, we could send a message to an object and let the object figure out how to handle it. It turns out that the ability to perform late binding is crucial to manipulating families of types and to object-oriented programming. The basic idea is this. You create a base class which defines the common interface to a family of types. Then you write a program which only uses the features of the base class. When you derive new types from this base class, you can redefine the behaviors of the new types. The program doesn't need to be changed, since it only uses the features which all types in the family must have. And here's the catch. When your program sends a message to an object, the object determines at runtime what to do with the message.
Not only does this make your code easier to read, write, and maintain, it lets you extend the system. You can add new types just by deriving them from the common base class. So in this lesson, we've seen how to build hierarchies in C++. We've also talked about the need for late binding. In the next lesson, you'll see how late binding is used in C++ and find out what polymorphism means. So stay tuned.
In the last lesson, you saw how families of types with a common interface in the base class and different implementations in derived classes model problems you want to solve. We also saw that the most convenient and clear way to deal with these types is through the common interface. For instance, we want to be able to tell a pet object to speak and let the object worry about how it's going to speak. We also discovered the need to delay the binding of a function call until runtime. This is called late binding. To make it easy to manipulate a family of types through its base class, object-oriented languages have late binding built into the system. In C++, late binding is implemented with virtual functions. The special keyword virtual tells the C++ compiler that it should not bind any call to this function at compile time, but instead delay the binding until runtime. Let's see how this works in the pet example from the last lesson. 3 changes have been made here. The addition of the virtual keyword is only necessary in the base class. Any derived class which has a function with the same name and prototype will also use the virtual mechanism. We've also added a new function sit. The third change is in the function talk, which now takes a pet pointer rather than a dog pointer. If speak was not virtual, the member function call inside talk would only call the base class version of speak. Since it's virtual, however, the compiler performs late binding. The actual function called is determined at runtime based on the type of the object. There's some other changes we can make. We can call a virtual function when an object is passed by reference. Now we can create a group of different types of pets and treat them as generic pets. In this line, an array of pet pointers is built using aggregate initialization. Notice that automatic counting is used to determine the size of the array, and the objects are created on the heap with new, which returns the address of each object. Since dog, cat, and bird pointers are also pet pointers, the return values can be assigned directly to the array. The next line calculates the size of the array as a constant, which doesn't use any memory. The advantage to using automatic counting and this constant calculation is if you want to add more pets, you only have to do so in one place, the aggregate initializer list. The remainder of main simply calls the 2 talk functions for each object in the array. Note that we must pass an object, not a pointer, to talk to. To see that late binding does indeed take place, we can step through the program using the Integrated Development Environment debugger. You can see that even though both versions of talk only know that they're getting pets, they call the correct implementation of the speak function in each case. You're probably wondering how late binding can take place. In the workbook for Lesson 18, you saw a crude installation of type information into objects. It seems that for late binding to occur, an object must know what type it is, which requires an extra data member. Let's look at the sizes of some objects. This program looks at the sizes of 6 classes, each of which contains a single int as member data and 2 functions f and g. We are looking for a difference in size when one or more of the functions are virtual. Notice that we use stringizing and string concatenation in the macro to reduce errors and repetition from typing all those printf statements. Here is something interesting. Whenever a class has one or more virtual functions, the size of that class is increased by 1 pointer size. This secret pointer is called the VPTR, or vPointer, and is the way the object knows what type it is. Here's how it works. The vPointer contains the address of an array of function pointers. This array is called the vTable. It contains addresses of all the functions which are virtual. Each derived type has its own vTable. When an object is created, the appropriate vTable address is inserted into the object's vPointer. When you make a call to a virtual function, the compiler doesn't execute a normal function call, which is an absolute call to some address. That would be early binding, which is what a C compiler always does. We don't want that here. Instead, after it performs the usual type checking for a function call, the compiler inserts a special bit of code. This code says, go to the address pointed to by the vPointer. Index into this array by x places and call that function. The exact function body called is determined by which vTable address is in the vPointer. Notice also that the order of functions in the vTable is critical. Since the compiler calls the function by indexing into the table, all the vTables must have the same order of functions. However, you don't need to worry about any of this. The compiler takes care of it for you. Because all virtual function calls are made through the vPointer, it is critical that this pointer be initialized before there is any possibility that a member function can be called. The only place this can be guaranteed is in the constructor, because the compiler ensures that a constructor is always called. Thus, it is the constructor which establishes the specific type of the object and its future behavior by its insertion of the proper vTable address into the vPointer. In this lesson, we covered how C++ implements late binding with virtual functions. In the next lesson, we'll look at the way to build and extend programs using type hierarchies and virtual functions. You now understand how to use object-oriented features in C++ to create new data types, either from scratch or from existing types with inheritance and composition. Manipulate objects through a common interface to a family of types, and dynamically create objects at runtime. However, an object-oriented program does more than just use one of these features. In this lesson, we'll look at the process of building object-oriented programs, which are easy to write, read, maintain, and extend. In the view of modern business thought, you must know what business you're in. This doesn't mean what product you're making, or that you're in the business of making money. It is the answer to the fundamental questions. What need do you satisfy? Why do your customers keep coming back? If the world changed completely tomorrow, why would you still be in business? The answers will reveal the underlying concept that pervades your business and explains your success. You're not in the telegraph business, but the communication business. You're not a receptionist, you create and manage messages. You don't sell products, you satisfy customer needs. The difference may seem subtle at first, but once you understand the basic meaning of your company, you can make clear decisions about its design and direction. The same thing is true when creating an object-oriented program. With study, you can see that all programs, even the most complicated ones, have a single fundamental purpose. Because programs can be obscured by their details, it is sometimes hard to see exactly what this fundamental purpose is. In procedural languages, it is often just a little too hard to think about solving a general problem, or a class of problems, so you end up with a program which only solves one problem. These kinds of programs are too specific. They are like a company which thinks it is in the business of making a product. A program which is designed to solve a single problem is very difficult to adapt to new needs, which probably means you will end up throwing it away and writing a new one. An object-oriented program, on the other hand, is built around a central concept expressed in the abstract base class of a family of types. It doesn't always jump out at you right away, but when you somehow discover the central concept, the design and implementation of the program becomes clear. You can easily make decisions while creating the program, and the final code becomes expressive of what the program does rather than how it does it. This means that a program is not only easy to read, but it's easy to extend when you encounter a new situation. You extend a program by deriving a new type from the abstract base type. Since the program only deals with the abstraction, it doesn't need to know you've created a new type. It just treats your new type like all the other types derived from the same base type. Let's look at the central concept using some examples. A video game is a collection of independent, interactive creatures. If you want to increase the complexity of the game, derive some new creatures. A spreadsheet is a collection of cells, each of which produces a value. The cell is an abstract base class, and all the specific types of cells are derived from it. Numbers, formulas, headlines, slides, macros, anything which is convenient to arrange into cells. A spreadsheet is simply a way of organizing complexity. Notice this doesn't restrict us to viewing it in ways other than a two-dimensional array of blocks. A calendar is a dictionary of events. This is a specific type of dictionary, a class which stores, sorts, and finds a set of objects. An air traffic controller manages a collection of flying vehicles. Adding a new type of flying vehicle is simply a matter of deriving a new type. Any one of these programs can be tremendously complicated, but each one still has a single fundamental concept, the business that it's in. Recognizing this concept means recognizing the abstractions in the problem. Once you do that, you can create the common interface, the abstract base type, for the family of types which represent your solution. The primary concept of a program isn't always immediately obvious. In Lesson 18, for example, we started with a class called Dog, and later realized we were dealing with pets, not just dogs. This meant that Pet became the abstract base class. Often, you will discover the fundamental concept of a program only after you've worked with it for a while. This is part of object-oriented programming. Design is a dynamic, ongoing process, and you can't always know everything about a problem before you start writing the program to solve it. Let's take another look at the pet example as we left it in Lesson 19. Even though it doesn't make any sense to create an object of class pet, because the class isn't specific enough to create a meaningful object, you still can. You shouldn't be able to because the class is truly abstract. It's only an expression of a concept, not a specific type of pet like a dog or cat. In C++, there is a way to prevent the end user from creating an object of an abstract base class. This is called a pure virtual function, and you create it using the pure specifier. The pure specifier simply says there is no function body for a particular virtual function, and you state it by assigning the function body to 0, like this. Now, pet is a pure abstract base class, and the compiler will generate an error if anyone tries to make an object of type pet. If one or more of the virtual functions in a class are defined with the pure specifier, the compiler doesn't generate a vtable for that class. Thus, if you try to make an object of that class, the compiler cannot find a vtable address for the constructor, and it complains. Since pet is a common interface to all types of pets, we can now easily extend the program without modifying the portions of the program which work the abstraction of a pet. To add a new type of pet, called a hamster, we just derive it from pet. Class hamster looks just like all the other classes. The functions talk and talk2 are unchanged, and most of the main is unchanged. Notice the place which is changed, however, the point of creation. It isn't enough just to create a new type, you must also create an object of that type. The point of creation is where the object's behavior is established, that is, where its v-pointer is bound by the constructor. Thus, there's always one other place where you must change a program when you extend it, the point where the specific constructor call is made. We can't have any hamsters in our system unless we call the hamster constructor. Any program where you have a base class which provides a common interface is extensible. This means you can easily add functionality by deriving a new type from the base class. All programs in use must be changed to adapt to new needs. And changing programs has always been very expensive. In object-oriented programming, however, this process can be almost effortless. All the changes are isolated in one place, the extensions you add during inheritance, so introducing new functionality doesn't mean breaking old code. Since the cost of software maintenance has traditionally been 1/3 to 1/2 of the cost of the program during its lifetime, this has tremendous financial benefits. In addition, the expressive power of object-oriented programming amplifies the individual programmer's productivity. This is hard to quantify, but some programmers feel it is as high as 10 times. In this lesson, we looked at how to build object-oriented programs that are easy to write, read, and maintain. In the next lesson, which is the final one in this course, we will look at some of the other features of C++.
Well, I guess this is it, the last lesson. Over the past 20 lessons, you've learned a lot about C++, creating new data types, inheritance, polymorphism, and dynamic object creation. Not to mention the other important features of the language like collections, function overloading, constructors and destructors, type-safe linkage, data protection, references, constant inline, static members, untagged enumerations, and code organization. Whew! With all that you've learned, you now have the knowledge you need to write object-oriented programs in C++. But you should also know that the language has many other useful features. For example, operator overloading lets you define the behavior of operators when used with objects of a class. This is especially helpful with the equal operator. This example defines a graphical object, point, that uses operator overloading. Class point has an x and y location. Since point is a mathematically oriented data type, we may want to use it in equations rather than calling member functions in the ordinary way. We can do this by using the operator keyword to define behavior for the equal sign and the plus sign when used with objects of class point. Now, when the compiler sees a point on the left, followed by a plus sign, followed by a point on the right, it calls the member function operator plus for the object A, with the object B as the argument. Similarly, when the compiler sees a point followed by an equal sign followed by a point, it calls the member function operator equals for C. Operator overloading allows you to create your own natural syntax when using mathematically oriented objects. During some of the exercises, we talked a little about multiple inheritance. But there's more to it, and it isn't as simple to use as single inheritance. Although you can often avoid using multiple inheritance, sometimes you need to combine features from two dissimilar classes which you didn't create yourself. Here's an example. Suppose you have a class which can store itself on disk, and some system to manage the storage of that class. Now suppose our old elevator class was written by someone else, but you want to be able to store it on disk. Without multiple inheritance, you would be in for a hard time. But with multiple inheritance, you can simply say an S elevator is storable, and it's an elevator. You must explicitly initialize the two pieces of the new class, called subobjects, in the constructor initializer list. Although you can call Storable's version of the store function, it probably won't do the right thing for an elevator, so it needs to be redefined. Programming takes practice, but we've given you the foundation you need to become a great C++ programmer. That's all I have to say. I'd stick around, but I really have to get this office cleaned up. Good luck, thanks for joining me, and go out and build some great objects.
Then go take a hike. It's back to C, and you will see, yeah.